Okay, so if you remember yesterday lecture, like today we're going to speak about the toy case, which is a Fourier-Mukai partner of E times F. This is a product of elliptic curve in characteristic P greater than 3. 2 and 3 are not prime anyway. So, okay, so it's because the elliptic curve in characteristic 2 and 3 present a series of problems that I don't want to dwell into, and so this is a thing. So the goal, so there is this theorem of Boltzmann. They say that if X is a smooth projective, over C, and dBx is equivalent to the derived category of the product of the complex elliptic curve, then X is isomorphic times F. And the proof with this, it's really used. He has a counting formula for Fourier-Mukai partner of abelian variety, which is the Hodge theory. So there is no hope of replicating in positive characteristic. So today we want this. So we have a statement about Fourier-Mukai partner over the complex number, and we want it in positive characteristic. Oh, and K today will be algebraically closed. So the strategy we have one. Well, first is X is a abelian surface. Two, transform the problem into a deformation plus lifting problem. And 3, solve the deformation So, well, one is just for today. This part will give you motivation on why Lieblich-Olsson deformation technique that I will explain next time is useful. Like this is general, like how you transform the problem into a deformation problem. And this is the reason why this is a toy example, because we didn't, even if the paper was already out, we didn't use it, but we had a way around it, and then but then if you really want to do, so this part just worked for product of the elliptic curve, and it's something ad hoc, but I think it's worth it to present, because in the toy case you see what problem you can encounter and what problem you have to solve. Like it's not just you transform in a deformation problem and then everything is easy. There are some technical problems around. Okay, so let's start with one. And one use characteristic P techniques, but they are really easy. So one is, well, derived equivalence conserve dimension and order of the canonical bundle. And this is it's a consequence of Orlov representation theorem that work over any field. And so it's working characteristic P. So what we have is that X is a surface and omega X is trivial. And then I will try to do like that. And so the step 2 actually is due to conics. That in her PhD thesis, basically, she showed that so derived equivalence induce isomorphism in cohomology. And in characteristic P, you can have isomorphism in crystalline cohomology or in étale cohomology. And we're going to use étale today. And the thing is, these isomorphisms mix up the degrees. And so you don't have really control on what happens in the degrees. But for surfaces, so there is two things. It preserves parity of the degrees. And in surfaces, once you preserve parity, there are Poincare duality. Many invariant can be recovered by a derived equivalence. So basically, Honix tells you if L is different from P prime, we have an isomorphism H1 étale X Q L plus H1 X étale H3, sorry, it preserves the parity, with H1 E times F QL étale plus H1 E times F étale QL. But then Poincare duality. H3? Yes, thank you. Right. So Poincare duality tells you that they have the same B1, and then you use Bombieri-Mumford. Tells you that X is an abelian surface.
There's only K3 and the name characteristic, right? Naming characteristic on the K3 and the billion.
Yes, so it's the bet is what distinguishes K3 and abelian. You have to be careful because if you're in characteristic 3, then there are bielliptic surfaces that have trivial canonical bundle and numerically look like abelian surface. And then, so this works because the bet it's B1, but one has to be careful with the invariant because so one of the reasons why it's difficult to work with bielliptic surface in characteristic 2 and 3 is that it's not yet known. So a bielliptic surface, you take the canonical line bundle and you take the cover, and in characteristic 5 and above, this is an abelian surface. But it's yet not known if in characteristic 2 and 3 this is an abelian surface because it could be another bielliptic surface with trivial canonical bundle. So yeah, so that is why it's a forest I don't want to go into without someone that know really well how to work in characteristic 2 and 3. Okay, so what we're done with one. Two, transform the problem into a deformation problem. Like, suppose that we can find A and R is like yesterday. Complete devoir, blah, 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 blah. With residues field equal K and of characteristic 0, such that one A K is E times F and X, like the closest fiber. So these are lift. So we found two lift of E times F and X, such that this happen. And then we want that the generic fiber, let's say it's a product of elliptic curve. And 3, you want that the generic fiber should use the right font here, are derived equivalent. So suppose that you can cook up this thing. And how we cook up this thing, it's going to be 3. Then what happened is we can base extend to C and get an equivalence of complex if A eta is a product of the elliptic curve, this is going to be a product of elliptic curve. And so we can use Solzna and deduce that A, C is isomorphic to X, C.
Should this be curly X, C?
Yes, thank you. And also, yes.
So you embed a fraction field into complex numbers?
Yes.
And you can always do that?
Yes. Well, let's assume that the cardinality of P is less or equal to the cardinality of the complex number. Yeah. and then so yeah, these are isomorphic, but then you have, and then okay, I promised myself that I will be brave and use the derived device. Don't comment on my technique. So it's in Scandinavia we use a sponge that is wet enough to clean, but not too wet that need to be drive afterward. I know this sounds horrifying, but now I'm used to that. And okay. Okay. So okay, so now what we do is if we have that isomorphic, but so basically we have there is an extension field of the quotient ring of R, the field of quotient of R. There is a finite extension that between there and C, in which A and X, and it should be curly X also then. A and X should be isomorphic. So there is L finite extension such that L Q of R. R is my ring, and Q is a field of quotient. So that XL and AL are still isomorphic. Then we use a technique that is known as spread out. So what happened, we can take an extension of R, a finite extension of our ring, so that the quotient of R prime contain L. And what we do, we get two lift of A times F and X to R prime. And once we have this, so we have that A prime, we have that the residues field of M prime is K prime, which is actually a finite extension. So this is what it's finite. So it's a finite extension of our base field. But now we use that K was algebraically closed, so finite extension does nothing to it. So actually, this is K. So what we got two lift.
So you just take like R prime, which is like the integral closure of R.
Yes, exactly. So what we get two lifts of E times F and X with isomorphic generic fiber. And then you use Matsusaka Mumford. Use Matsusaka Mumford. They say that if you have R prime, devoir, not even complete, and you have D inside R prime and Y inside. I'm giving less general assumption of actually what they do. So if you have Z and Y, two families, so like two scheme over R prime, such that one, the generic fiber of Z is complete. Two, the DK and YK, the closest fiber, are algebraic with DK complete. And 3, YK not ruled. And 4, V eta and Y eta birational. Then YK and DK are birational. Okay, so whatever, suppose that the X is our Z and A is our Y. D eta complete. Well, D eta is an abelian surface. Check. ZK, YK complete algebraic. Well, they are abelian surfaces, and ZK complete. Check. YK not ruled. Abelian surfaces are not ruled. Well, they are isomorphic in our case. So they are birational. So YK and ZK are birational. So we have this. What happens when two abelian surfaces are birational?
Isomorphic?
Yes. So they are isomorphic. So we get, as a consequence of all these things, we get that X is isomorphic to E times F.
Can I ask about this algebraic condition? So this morphisms are morphism schemes, right?
Yeah.
So how can they fail to be algebraic? What does it mean?
I have no idea. It might be that they are in a more general setting. So yeah. So yeah. So it's this paper is really general, and this is what it's Matsukatsaka manifold 1, because then they have, so in these you prove birationality, but then if you have an explicit birational map satisfying property, you have Matsukatsaka manifold 2, which give you an explicit birational map at this level. So yeah, it's awfully general paper. So. Okay, so we get X isomorphic to E times F. Notice that if I didn't have K algebraically close, we'd start with, I could get here, but instead of X and E times F, I have X base extended to K prime and E times F base extended to K prime. So what I get is isomorphism up to finite extension. Okay, this is too low.
Here we were using A equals K bar. One, we're working over a non-algebraic close to K. You still spread out over.
Yes, it's
over
what I said.
Extension?
Yeah, it's what I said. But the thing is, the final result will be up to the finite extension.
Okay.
So this is.
Okay.
So the thing is, you have isomorphism, but not defined over that field. The isomorphism is defined over a larger field. So if you have a finite field, then it will be a finite field of higher over another finite field of higher order.
And the issue there is because of Matsushita's theorem or because of the spreading out?
It's spread out.
Okay, okay. You might need to ramify this.
So the thing is, yeah, so it's because we have to take this finite extent, like since we have the result, we start from a result on the complex number. And so we have to base extend to C. Then C is too big. Like once you base extend to C, you can say, okay, I don't have to go all the way to C. I can reduce myself to something in the middle. But I have to, like, I don't know that my isomorphism will be defined on my field of quotient of R. This is.
So in this spread out, I mean, I know this technique where usually you get something that is finitely generated, but not necessarily finite.
No, but so this is the thing is L is finite.
Oh, so, yeah, but how do you get a finite?
Well, it's because you have two objects, so everything is algebraic. So you have two things and an isomorphism over an algebraically closed field, and two things that live over another field. And up to a finite extension. So think on characteristic 0. So it's you take finite extension. So if you have two objects in an isomorphism defined over Q, so two objects defined over Q and an isomorphism over the complex number, you take a finite extension of Q, and like up to a finite extension of Q, that things will be.
But as I said, I mean, I see how to get that for finitely generated, because you take all the coefficients of like that show up in the isomorphism. But how do you get it for finite? What do you mean finitely generated?
Yeah, I mean finitely generated.
Oh.
Algebraic extension.
Finite only applies to
it's because
so
I want K equal K prime, so I don't need to go to all the algebraic closure to Q. Yeah. So okay, so now we have our strategy. We have, oh no, I erased it, it was here. What we have to find is two lift so that the geometric generic fiber are still derived equivalent. And one has to be, the generic fiber has to be a product of elliptic curve. This is the nice thing. So now we are in 3. Solution of the deformation problem. And okay, so good news. What is HU of the tangent of an elliptic curve? Dimension 1 is an HU is 0. HU of E over E is again 0. So elliptic curve lift and they lift line bundle deform. So we can deform. So what we get, we have the same is true for F. E, call it double. We are going to force X to deform. So the product of elliptic curve deform over the bit vector because there are no obstruction whatsoever. And of course, we're going to force X to lift to the bit vector, which makes sense because at the end X will be just isomorphic to the product of the elliptic curve, so it will lift to the bit vector. So we have lift of E and F.
So they are not unique, just take any list. Right?
Yeah, like and then when we go when both are ordinary, they will be the canonical lift. But yeah, so we have lift of E and F. And okay, so we take our A to be F. And these satisfy what we wanted. So it's deform the product of E times F, and the geometric generic fiber is a product of elliptic curve. Observe that this is a highly not random deformation, because the deformation space of a abelian surface is dimension 4. Then if I want to lift a line bundle together with it, I get the dimension 3. But this dimension 1, dimension 1. So I am creating something. So this lives in a dimension 2 space in the moduli space. So it's a highly specific deformation that I'm getting. Now the problem now is to lift X in a compatible way. And the idea is that you have to use derived equivalence like a chain. So E and F, they chain X with the derived equivalence, and when they deform, they bring it with them. So this is the idea. And today, we really use derived equivalence. But with with Lieblich-Olsson result, you really deform the equivalence, like the given equivalence deform along. It's so we just prove so in this today we just prove that at the end the geometric fiber are derived equivalence, but we don't give a specific derived equivalence that restrict to the one that we had, but with Lieblich-Olsson technique, you really deform the derived equivalence. Yes?
Sorry, this is an elementary question, but I can't sort it out in my head. What would the space W being the same in both maps?
Well, it's the bit vector. Like I'm using the bit vector.
Oh, those are the bit vectors.
Yes,
it's a deformation which lifts them.
Yeah, because I am here. And so the word is easy for curves. So I have no problem whatsoever.
This is bit of W.
Yeah. So okay, so now half an hour. Let's see if I want to cut something. Well, okay, so now so the difficult part is find a compatible deformation of X. So what we're going to do is we use let's explain the strategy, and then maybe I will say more about a specific step if I have time at the end. So the idea, so what we prove, and then I will say more of this if I have time, is that X is, X is isomorphic to a modular space of vector bundle of E times F. So this is something that we prove in the middle, and actually this works for any for any two, it's more general. So what you really have is here, if you have two abelian surfaces that are derived equivalent, then B is isomorphic to a moduli space of vector bundle on either B or A or the dual of A. And of course, in this specific case, the dual of a product of the elliptic curve is isomorphic to its, they are self-dual, so it's, we can avoid this. And so in Lieblich-Olsson paper, in which they, the first one, in which they study Fourier-Mukai partner of K3 surface in positive characteristic, the first one. So a statement of this type is, it's like one of the technical heart of the paper, because life is it's more complicated for this for K3s. So the idea is that the idea behind this is that Orlov representation theorem, every derived equivalence is given by a kernel on the product. And so for a abelian surface, this kernel is a shifted sheaf. And then you look how this equivalence behave in cohomology. And so if you send if you send the Chern character of the Mukai vector of a skyscraper sheaf to a Mukai vector of a skyscraper sheaf, well, you know that it sends a skyscraper sheaf in a shifted skyscraper sheaf, and directly, like if you need to read Daniel books, it's one of the results there, you get an isomorphism. Like you really get an isomorphism. So what you have is that if in cohomology, if P, like you have an equivalence P from BBX, I want to do it in this direction. Yes, in this direction. And you look what happened at the corresponding mapping cohomology. If this is 0, 0, 1, then you have that X is isomorphic to E times F. And then on the other side, if phi 0, 0, 1 in the general case is something like this, with this is an element in the Néron severi, then you play with autoequivalences. And so you can assume that R and the characteristic of the base field is 1. So if it's already co-prime, you're fine. If it's not, then what you do, you make chi co-prime by tensoring by a line bundle with the characteristic. Like you make chi co-prime with R, and you can do it because this is isotropic and primitive, and there is OS. So you have another vector which against this vector give you 1. So with the Chinese remainder theorem, basically you can show that you have chi that is co-prime with the base field, and you use the Mukai duality induced by the Poincaré bundle to swap R and chi. Okay, and after that, and so R and pi equal 1, and L ample. So you can play along and have these two things. This is a safety net because then now you can consider the modular space of
So you're saying pick R co-prime with the characteristic? Is that what that's?
Yes.
Okay.
So the thing is, you can force it to be co-prime with the characteristic,
Yeah.
and L ample. And then you consider the modular space of stable vector bundle with respect of L and Mukai vector are L chi. So, wait, no, I mistake. I forgot the last part. So now you consider the modular space of vector bundle the modular space of vector bundle I think, of course, I reverse the order there. Let's see. So I consider the modular, sorry. Everything works, it's no matter, because if I have an equivalence, then I have the other equivalence. But this is the one. No, I want F, so yes, no, it was okay. I always get confused. So now I construct the modular space of G-Zeker stable vector bundle of Mukai vector R on L chi. I'm not going into this construction. You have to have a little care about non-emptiness in characteristic. So this is a construction in characteristic P. So one has to be pay a little attention. And the reason why we choose this is because then we don't need to pay so much attention. So it's what's so. So you construct that, and this has a universal family. So the numeric tells you that this has a numerical family. This has a universal family. It's a fine U, and then you can consider the integral transform let's call this M for now. And this send R, L, chi to 0, 0, 1. But now you have your equivalence with dBx. You have 0, 0, 1. With the composition goes to 0, 0, 1. And so you have that X is isomorphic to M.
So it's the same proof as for K3s, right?
Yes, exactly. With the thing is that, so Lieblich-Olsson deformation technique was created in order to prove the first part, that if the 0, 0, 1 goes to 0, 0, 1, then X is isomorphic to Y. So this is how they created the deformation technique. It's because Fourier-Mukai equivalence between K3 surface, the kernel is not a shifted sheaf. And so you don't know that if 0, 0, 1 goes to 0, 0, 1, a skyscraper sheaf goes to a shifted skyscraper sheaf. But we do. And so this was like one line. And realizing this was what to get us started. Like, wait, yes, we can do this. Like the technical part there is just we can take it away and it's one line. And so okay, so you have these, and then the idea is okay, I have a lift. I consider the relative moduli space. the relative modular space and these should specialize to X. But there is a problem. Can anyone see the problem? I have to be able to lift, so this L was a class of a line bundle. I'm deforming E and F, so this is like, I have to be able to lift this class here, and then to the like it has to correspond to a class in the general fiber in order for this to work. If it does, then the vector of, so when I restrict this to eta, I will get a primitive vector with the right numeric, and so I will get that if I can lift L tilde, then let's call this really curly M, then M eta will be derived equivalent E W eta. So if I can lift, then it will be I will get my specialization so that the general fiber will do the deal. So everything now is reduced to be able to lift a specific line bundle on from on the product of the two elliptic curve to the lift. And okay, so there are three cases: E and F, ordinary.
So do you still have any freedom left in choosing that?
Well, I can choose E and I have E and I can choose. So basically, it's yes. So it's I have L. I have to choose lift of E and F, so that L lift. So thank you for asking. So it's the freedom. Like I have a two-dimensional space here, which I can choose. So I have some freedom. So E and F are ordinary. So is E times F, and ordinary abelian surface have a canonical lift. And we have, by the universality of the canonical lift, we have that the canonical, so E and F have canonical lift, E can and F can. And what we have is that E can W F can is the canonical lift of E times F. So the canonical lift of the product is the product of the canonical lift. Okay, so do you remember a nice property of canonical lift? What happened to the Picard group when I have the canonical lift? The specialization map is surjective, which means that I can lift L to Z. So, okay. So we have that. So we have that econ W can subject E times F, and then we conclude. Okay, so now if
sorry, can I check? Did you mention last time this is actually isomorphism?
yeah, no, I didn't, but yeah, and it's always the specialization map is always injective, and in this case it's surjective.
Oh, I see.
And so it's
so
it means that I can lift L. I can lift L a class. Now, if we have two, so let's suppose that F is supersingular. And then in general, for any, we have the Picard of E times F is the Picard of E times the Picard of F times the homomorphism between E and F. Isogeny, morphism of elliptic curve. Okay, but then if 2A, if E is ordinary, we have that there is no isogeny between E and F. Okay, but then a line bundle on the product is the pullback of two line bundle of the elliptic curve, which I can deform. So any E and F work. Okay, 2B. Both E and F are supersingular. At this point, we use, so we have that hom E and F is different from 0, like two supersingular elliptic curve are isogynous, and it's more given L different from P prime. There is psi from E to F, isogeny of degree L to the n for some n. So the isogeny graph of elliptic curve of supersingular elliptic curve of degree L is connected. And this is not our result, actually it's a result in cryptography, like that saved us because we were really struggling with this. And then, so the idea now is that you can, by again post-composing, pre-composing with auto-equivalence, you can assume that L is a class of a pullback of a line bundle on E times the pullback of a line bundle on F times an isogeny psi, and this is a Poincaré bundle on E times E, or Mumford bundle on E times E. So this is how the isomorphism here is given. So it's pulled back from something of E, pulled back of something of F, and pulled back by an isogeny of the Poincaré bundle. So you can assume that this is like that, and psi as degree of psi and P are coprime. You can, so if it's not coprime, you post-compose with things, and you can get again Chinese reminder theorem over and over. You get to this condition, and now you use Grothendieck. So this tells you that psi is étal. You can lift étal covers. So basically, if you have an étal cover, you deform the base, and there is a deformation of the top, such that, and a map between the two étals that restrict to yours. So what you do, you deform. So you have F, you any lift, and then E, F, W. This is the étal cover lift induced by psi. But then you have this guy here that is the only one that is causing problem, lift to this specific. So
sorry, this last part of that line bundle, the Poincaré bundle lives on E cross E, and psi goes from E to F. What is psi upper star of E?
Because sorry. Yes.
So then you take the Poincaré bundle on F cross F, or on.
Let's see. I have psi. Go from E to F. Yeah, I always swap things. So yes, thank you.
Yeah, okay.
Yes, I always. There are two things that can be swapped. I swap them. So you see how this works when I teach fraction, in which I swap numerator and denominator without reason. So see from So this, which is the only one creating problem, lived actually here, because the Poincare bundle it lived, like it's there is nothing more universal than the Poincare bundle, and so at the end we have this lift, and this lift, because these are just line bundle on the curve, and so this class, the interior lift to a line bundle, and so we take that class. So we have that 1 times psi after psi, the Poincare bundle on f times f lift. And so we conclude. So you see, it's the first part is really general. Like if you find specific lift of your variety that such that they're still the generic fiber are derived equivalent, you are done. And then you have to find the specific lift. And so for next time, I want you to remember. So for tomorrow, this part about like this is why we are trying to find specific lift of our variety. And well, I should have said more for that, but the fact that you can lift a tile cover. So this will be needed in the last lecture when I present application to Enriquez and bilectic surface, because we deform an Enriquez surface and we force a deformation of the canonical cover. This is how we study Fourier-Mukai partner of bilectic and Enriquez and for the bilectic we do the same with the Abelian cover in positive characteristic. Okay, so sorry, 5 minutes late, but I will stop here.
In that case, the final statement true for non-closed fields that Fourier-Mukai partners of cross F are isomorphic.
I would not know. Like it's the thing is, even the easiest case, a finite field. The thing is with I would not know. Like the thing with this technique, I get just up to an extension, and so yeah, I would not. And this is also like when Katrina, when she studies the Picard, the Albanese variety of Fourier-Mukai partner, she gets that they are isogenous up to a finite extension. So it's so non-algebraically closed fields are. I try to leave them alone and not to show fear if they are around.
like a bee or a wasp. Yeah.
Yes, like I'm dying inside, but I do not show fear, and then sometimes they go away, and I'm happy and keep doing my thing without them.
Any other questions? If not,